Thank you very much. Yeah, I'm particularly excited to speak about a real frontier in physics. This is the diffraction limit, and the diffraction limit is a property which keeps us from being able to see details of the nanoscopic world with light. So I'm very pleased to talk about it. I'm particularly excited because we just found a little startup company to try to exploit what I'm going to talk about to some extent. But it's more an educational talk, so I will keep that short. Before I really start, actually, because George mentioned that the flat solar packages on the roof are very effective. I have put one on a small house in North Germany, which is not much better in terms of weather than the UK, and it's brilliant. It's giving me about 65% solar harvesting for hot water and heating across the year, so I measure that. So it's actually quite working. Okay, so let's go and delve directly into my talk. I promise you to talk about the diffraction limit, and I will, of course, explore and look into what that actually is and where does it come from. But before I do that, I would like just to compare what we can typically see. This is basically the length scale of objects which we just about can see, starting with an end on the left side of the size of a few millimeters. Human hair is typically 1/3 of a millimeter, 300 microns on that scale, and we can definitely see the hairs. Even my ones get thinner all the time, so it becomes more and more difficult to see them. Cells would be typically on a scale between 10 microns and 100 microns, but we talk about the outside of the cell. And in order to understand biological mechanisms and to have a biomedical approach, we need to be able to look into the cells. We want to understand the mechanisms which happen in the cell, because that would be a real advantage and would improve the medical treatments and diagnosis quite a bit. So then bacteria would be between 1 and 10 microns, and cell organelles, for example mitochondria, would be another order lower. And this is exactly what we can just identify. So you see the dotted line, and this dotted line is roughly positioned where the diffraction limit of visible light is positioned. So this diffraction actually keeps us from seeing details, for example, within a mitochondrion, but it also basically makes it impossible for us to even identify viruses, proteins, and especially small molecules. So small molecules would be of a typical scale of maybe between half a nanometer and a few nanometers. So in order to understand, for example, protein-protein interactions, and they're quite important for our body, for example, to see them directly would be, of course, quite a help, but this is a quite difficult story, which I try to illustrate. All right, so this is actually, these are 3 different viruses. This is polio, influenza, and swine flu. And the interesting bit that you can easily identify them visually. The point is, as we just learned, that their size is actually much smaller than the diffraction limit of light. So we can't just look at them and identify them this way. We have to do that by testing. Typically, we look into the binding sites. We look into certain reactions of of a particular virus, but we can't see them in an in vivo or in vitro system. So not in a patient, for example. What we can, of course, do is we can use an electron microscope, which is far better in resolution, and then we can see them. And these artistic renderings, actually, which you see here, are actually done using electron microscope images as a basis. The point is, whenever we talk about electron microscopy, it has to happen in vacuum. It has to happen cryogenically fixed. And that moment, we learn nothing about mechanisms anymore. And basically, all in vivo or in vitro treatments can't happen. So, what is actually the diffraction limit? Where does it come from? So, in the simplest way, I can explain that the diffraction limit stems directly from the nature of light, which is not just a particle, but because of the dualism, is also a wave. And we know the wavelength of light is somewhere between 400 in the violet and 700, 750 in the deep dark red. So that means if we have a wavelength which is several hundred nanometers, we will have difficulties, imagining that as a wave, to identify objects which are much, much smaller than the wavelengths of light. So I can be more explicit. I can also give you the equation which govern that. But basically, what happens if we try to image something which is much smaller? For example, think about a single molecule. A single molecule which is capable of sending light, of emitting light. This molecule could be, as I said earlier, maybe just a nanometer. If we image that through a normal microscope, that 1 nanometer object will be, because of the diffraction of light, will be imaged onto something which is called the point spread function, which you see here on the right side, or which actually is illustrated here. So instead of getting a point, or even a blurred point, we actually get a diffraction pattern, which has a central maximum and also fringes, which are maybe better visible here. And this is just for a single bright spot, a single molecule. If we have a picture, for example, of a cell, and we have stained the cell, so we get light from all parts of the cell to identify the cell, all these little dots would individually create such a diffraction pattern, and all these diffraction patterns would overlap. And that means the picture is so blurred that we can't see the details far below that diffraction limit of light. Well, there are a couple of important physicists who looked into that more closely. One of them was Ernst Abbe, who actually worked for Zeiss more than 100 years ago. And he and Airy decided that you can actually calculate this diffraction pattern. And if we leave out the fringes, we just talk about the central maximum, then the half width of this maximum, the delta x, is roughly 0.6, which this factor actually stems that we have a circular aperture in a normal lens system. Usually the barrel is circular somehow. And then that's a more important bit, lambda over Na. Lambda is the wavelength of the light. Na is a numerical aperture. And for the sake of simplicity, the numerical aperture is measuring the angle of the acceptance cone. So the more light from different angles we can collect, the sharper our image will be. And the numerical aperture is actually the most important function. If you look on a microscope objective, you just screw that out and have a look, there will be always the numerical aperture stated, because this is the only important value on that objective which tells you anything about the resolution, the true resolution of such a system. Okay, the Airy pattern doesn't tell you really the resolution straight away, and there are different concepts one can use to illustrate that. So the Airy disk itself is shown here on the left-hand side. You have a maximum and you have some fringes, and now the question is, when do we say that two objects are resolvable? So let's say, for the sake of simplicity, we have two identical fluorophores, two identical molecules which emit light. So how close can we permit these two molecules to come before we say we can't resolve them anymore? And this is, of course, directly related to the pattern, and especially to this big central maximum in this pattern. So actually, Rayleigh had a criterion where he said when the maximum of the first falls exactly onto the first fringe minimum of the second, then as we see the superposition of the two still becomes resolvable, because we can see there's indentation here, which shows here on the side view, which is the cross-sectional side view of the light pattern. So this is just intensity in the vertical axis. Well, this is basically just looking onto the pattern we get. And we can say, yeah, we can resolve that still. And then Abbe phrased another one, and then Sparrow phrased actually exactly the condition in which our ability to resolve the two is vanishing. And interestingly, the only thing these criteria do is change the factor from 0.61 to 0.5. So the differences are really negligible. So what can we say? We can say that basically, if you just go back for a second, basically, this is close to a half. That's the wavelength. Numerical aperture in air can be at best close to 1. So if we look at that equation again, the rule of thumb is this is lambda over 2. So half of the wavelength of the light we're using is typical the resolution maximum we can achieve. Okay, what can we do about that? Obviously, this is not, would be a very boring talk if we say, look, that's it, sorry, we can't do much about that. And this is essentially now an Irish story, because Hachi Singh in 1928 was the first person ever to publish an idea which is circumventing that idea. The original idea is actually quite nice, the story, was that he used a gold particle, a very small gold particle, as a small emitter, and he placed the gold particle in his idea very close to the object and then scanned it across. And this is basically if you like, the origin of all scanning techniques nowadays. It's including actually electron microscopy or even TV, the good old ways, where a cathode ray was scanned across the tube, as much that this is the same principle as you use in atomic force microscopy or scanning tunneling microscopy. So basically he actually laid that down. He actually had another publication 2 years later in which he laid out that you can use piezo ceramics actually to scan on a nanoscale. So he's really basically one of the main origins for these techniques. Actually, he studied down the road. As we are on UCD, we have to say down the road. And, but he didn't finish the studies because he inherited a lot of money from his uncle when he died. So he stopped in the 3rd year because he said, don't need a certificate or anything. So he started to use it as a hobby and was very strongly working towards his goals. So in 1928, he wrote a letter to Albert Einstein. So we can connect the talks now. So Albert Einstein, who was a big shot at that stage, actually told him that basically the idea is useless. It would work, but the technology basically is not ripe and not mature enough to do anything like that. However, he indicated that this idea in itself has quite a merit and he should publish that. And then he published that, and then Einstein came actually with another idea, so they had it's a bit like twittering what they had. So a couple of days, they sent a letter in the good old times, and then a couple of days later, he got the response. So that was quite rapid, actually. So a couple of days later, he had a new idea. And then they had the second idea, which basically said, what about instead of a gold particle, we have a very small aperture, and we bring this aperture very close to the object of interest. And this is the idea of all scanning techniques, which are near-field techniques. So why is this actually working? And we see that on the right-hand side. So think about we have an optical fiber, just a piece of thin glass which is coated. So this might be just 50 nanometers across, for example. And because it's coated, the light will only emanate from the very tip. And then, of course, diffraction occurs, so we see the blurring in the side picture. But if we bring the probe closer and closer to the object of interest, so we reduce that, you see here, if it's close enough, there is no blurring, there is no diffraction really visible at that stage. That means if you bring your probe very close to the surface of interest and then scan it across, you can actually achieve data which is much more resolved than you would get in the far field of a normal light microscope. And that's actually shown here on the left-hand side. This is a confocal microscopy image that's already better than a standard microscope because it has an additional aperture in the system. So resolution of such a system is across 900 nanometer. And the same system has been used with such a scanning near-field optical microscope, as it's called nowadays. And you see much more details are visible on this particular system. And this is actually the original publication from 1928, which he published. There's a little bit of one drawback. Actually, he published 3 years later that the idea wasn't as good as he thought. And he shouldn't have published this because that takes a bit of the glory away, but he's still the first to clearly describe such a system. Actually, in fairness, it has been reinvented 3 times in the history because the people weren't aware of this publication, and then 30 years later, you hope they weren't aware. So at least we hope they had the integrity, but this has been reinvented several times before. Actually, Paul in the IBM labs in 1984 to 1986 actually devised such a working system. All right, so this is one way, but one way means you scan a sample which has its own complications. But we have a couple of Nobel Prizes which were awarded quite recently, so 2014, and interestingly not in physics, but in chemistry, but this is for political reasons and also that they have also limited places, only 3 people at maximum and only in one field, so you have to see how you get the people to receive a Nobel Prize. To make space for that, basically. So Stefan Hell from the MPI in Göttingen, Mörner in Leipzig. Stefan Hell got it for STAT, and Mörner in Leipzig actually got it for PALM. And to briefly illustrate what the idea is behind those techniques. So I said, if you focus down on a sample with a normal microscope objective, you're stopped by the diffraction limit. If you're far away, as a normal objective always is, the diffraction limit appears as calculated. But what about if we do the opposite? So Stefan's idea was actually to have a cone of light, which is like a donut shape, a ring shape, in which he is basically depleting the states so further states couldn't be excited. So he basically defines a circle in which in a given time frame, further emission of light doesn't happen, but for its very center. And this very center has different rules. So you can make this center, from which then the only light comes from, you can make that center much smaller than the diffraction limit of light. So this is the idea, basically. You have an exciting laser beam, and this is actually basically removing the light, or the ability to emit light. And then you have this inner one with another laser flash. You excite just the little hole in the middle, and then the light must come from that. But again, you need to scan. So this donut shape and also the second laser excitation must be scanned across the surface. That takes time and has a lot of drawbacks in that sense. Okay, so what about the other technique? And the other technique is actually, so this actually, you see what you can resolve. This is a confocal image actually of an artificial system. And this is what STAD is able to resolve. You see it's able to resolve objects of the order on about 30 nanometers. So another technique is actually, there's another example. You see the right side is actually made with a STAD microscope. The other one is a normal confocal microscope. But you see more details on the right side. Yeah, you don't always get 30 nanometers. Sometimes you get just 80 to 100 nanometers. You're 2 times better. And this is not really changing your life. So the other technique is PALM. And PALM is not a combination. The advantage of STAD is that it's deterministic. You define the volume from which light is going to emanate later on. Here you can make another trick. Well, let's suppose we go back to the Sparrow criterion. The Sparrow criterion was just the condition that we have 2 fluorophores being so close together that you can't distinguish them anymore. Just about. But think about the following. Let's suppose we have the ability to switch one of those molecules off. Then we see only one of them. So for example, this is the Sparrow case. Let's see we switch the right one off and only the left one remains. And we know the molecule is much smaller than the diffraction limit. So what the people are doing, they say, okay, we know this light is coming from a single emitter now, and this light must be from the center of the diffraction image. So they use a deconvolution, a mathematical deconvolution, to say the light comes from a much smaller object in the middle. And then they switch off this one and switch on other ones. And eventually they will also have switched on the one to the right-hand side and captured this position. There's, of course, one problem, and this makes it a non-deterministic technique. You assume that the light comes from a single emitter, and this assumption is, of course, not entirely valid. What you can do, of course, you can deactivate so many fluorophores that the probability of having one being close to another being still activated is very small. And that's basically what PALM is about. So PALM is deactivating the majority of fluorophores, getting only the positions of a few, and repeating the same thing thousands of times in order to make a much higher resolved image, which we see on the right-hand side. This is a normal microscope diffraction limited image. This is the PALM image of that. The same as this little section is actually enlarged. You see the details the PALM technology can render. And the same from this little object here, from this little area, you also get a lot of detailed structure information from that. Okay, so this is a beautiful technique. However, you have to be careful not to get artifacts. And secondly, you're not scanning, but you have to do thousands and thousands of these exposures in order to make your image. And that means, of course, that you're slow. You can't do real-time imaging. You can't do video rate imaging, really, because you have to do thousands of images in order to get one image. So what we have done instead, basically as an improvement, we designed small little nanoscale pixels, if I call them this way, which can be addressed. So we can switch these pixels on and off, and therefore basically remove the necessity to scan across the whole field. So what are these pixels about? First, they're plasmonically active. So that means I excite them in a particular way on a small thin metal film on top of a dielectric, and what I get is actually an oscillation of the electrons at the interface. This is the surface plasma. And this oscillation, of course, as you see here, this is a density oscillation, high density, low density areas. Of course, there's strong electric fields at these same high frequencies which are bound to the surface. And they have the same frequency as the light, and they have the same abilities to excite objects like small fluorophores. So this is now a way to address them. I just show you one, because time is running out. I'll show you just one simulation. There is one of those pixels, and you see that you can switch the excitation from this one to the next one in such a way. So basically, we are in a position to decide which of the pixels are lit at a particular moment in time, and we can encode information that we even can identify which pixel created which information if we put them together on a single channel detector like a photomultiplier. So we don't even need a CCD, strictly speaking, in the far field to get that pictures. So it has a couple of what we think are real good arguments. So it's compatible to normal microscopes. It has a resolution on par with the best systems which have been received the Nobel Price in 2014. And this is really the most important bit for us, it's fast. So we can do video rate or even faster than video rate imaging. It's biocompatible, we can do in vivo and in vitro imaging, and it's actually not that expensive to construct such systems. So, thank you very much.
Thank you, Dominic. Has anybody got any questions or comments? We've got a couple of minutes before coffee.
Coffee is of course dangerous now to mention the word coffee.
So maybe can I ask, how much faster is your technique than the kind of other stuff?
It is more than 1,000 times faster at the moment. And we hope we can actually make it much faster again. So in the moment we record video rate, but what we think we can achieve is something which we can basically measure on a sub-millisecond scale, so several hundreds or several thousand images per second, so you can really track the mechanisms.
If you draw out glass fibers, how small can you make it? You get all the light down to a smaller and smaller.
Yeah, you can drag it out. I've seen examples where the people reach something like 10 nanometers. The point is that this is not artifact-free. So actually, it's quite interesting. If you look into the publications, then in 2005, they had already something like 10 nanometers. And then the next improvement brought the 10 nanometers to 30 nanometers. I said, wait a minute, we were already 10. And that is the reason, basically, in the first years of this development of a scanning near-field optical microscope, the people were using it, but misunderstood where the information came from. And this is, if you think about having a bit of some transparent, some perspex plastic, and you look into that into a polarization microscope, you see all the colors. And these colors come from the stress in the material. You can bend it with your fingers, you see the colors. The same happens with the SNOM. That means a SNOM tip is very prone to actually see the stress on the fiber. So you have used your SNOM originally, basically in a mode which is similar to an AFM shear mode. And that is then the high resolution that people obtained first. Now, after another 10, 15 years, the people know how to handle that. They have shear force sensors on their scanning near-field optical microscopes, and they can do that more artifact-free in that sense.
Thank you, Dominic, again.